Hello and welcome to the computer learning class by Accelerate Computer Systems. My name is Arun and I'll be your trainer today. Today we will dive further deep into the ones and zeros that we learned about in the previous video. We have already talked about the ones and zeros in the previous video. We have discussed how computers work and what exactly those ones and zeros are and how they originated. If you have not watched that video, please watch it for better understanding. In this video, we are going to further elaborate on how computers they send information over Ethernet and why it is a 1 or a 0. Let's start by recapping what we learned in the last session because what we are going to learn today is closely linked to it. We discussed about the Morse code and that it uses the sounds D, which is a short stroke, and Da, which is a long stroke to be able to communicate. It has a code for all the alphabets. For example, the code for letter A is dida, for B it's da di did, for C it is da di da did, etc. Compare it to computers that use electrical, light or radio pulses to send information. For the sake of comparison, the sound da in Morse code can be considered as 1 and the sound D can be considered as a 0. In computers, when an electrical pulse is sent, it is considered a 1 and the absence of an electrical pulse is considered a 0. This is the very reason why it is said that the computers, they work with ones and zeros. In reality, the computers actually send and receive electrical, light or radio wave pulses and interpret these as either 1 or a 0. It is important to note that each of these ones or zeros is called a bit. Now this concept is very important. Remember that these ones and zeros, each of them is called a bit. And a group of 8 bits makes a byte. Bytes then make kilobytes, then they make megabytes, and the megabytes make gigabytes. Another point to note is that the process of using only two numbers, that is 1 and 0, by computers, it's called binary. We'll talk about the binary in one of the future videos because that is another important concept in computers. You might say, well, it is now understandable what is 1 and what is a 0, but how does it actually happen? Is there a way to see it in action? Okay, let's do that now. Let's check how information is sent across the cable. Before we go further, let's understand a few very basic things. Now we know that computers send pulses. Let us take an example of current, which is used in Ethernet to send and receive information. There are two types of currents that we have. One is DC or direct current, and the other one is AC or alternating current. The current that we have in our homes is alternating current, and computers, they work internally with direct current. And this is why it is important that we understand exactly how these currents visually look on a machine that is called oscilloscope. The video that you'll see now first shows how a direct current looks on oscilloscope, followed by alternating current. Please pay attention to the wave-like structures that you see for AC or alternating current. Let's watch.
So here we have an oscilloscope with the Y gain set to 1 volt per division and the time base set to 5 milliseconds per division. We have a 1.5 volt cell here. We're going to connect the black end of the oscilloscope to the negative terminal of the battery and the red part of the oscilloscope into the positive terminal of the battery. Now we're going to switch the polarity. So you have the red end of the oscilloscope going into the black terminal, the negative terminal of the battery, and the black to the red. So now we have a main supply on top, and we're going to connect the black end of the oscilloscope into the negative mains terminal and the red to the red. Now we're going to disconnect the black and the red, and place them into the element terminals of the main power supply.
All right, let's now summarize what we saw. With DC or direct current, the lines seem to be going almost straight, as you can see on the left side in the image. However, while measuring alternating current, we saw the wave-like structures. And that is because the alternating current, it moves in both directions. I'm not an electrical engineer, and even you don't need to be one to understand the basics needed to be able to understand how computers work. We should be able to visualize how DC and AC are displayed on the oscilloscope, because that will help us later understand some other very important concepts. We should also understand what a cycle is with reference to computers. In the above, when a waveform reaches a complete set of positive and negative value, it is called one cycle, and this is highlighted in white in the picture on the right. Now, what about DC or direct current? We see only a straight line. How do you measure a cycle then? Let's see this in the next slide. Okay, in DC, the cycle is achieved by sending two different volts. In the above picture, you can see that we are using 0 volts and 5 volts. Typically, the computers, they work with 3.3, 5 and 12 volts. As you can see, if 0 volt is sent, it is considered 0, as in the ones and zeros that the computers work with. And if 5 volts is sent, then it is interpreted as 1. It is important to know that computers use a clock to identify the number of zeros or ones while sending or receiving pulses. This clock is synchronized between both the computers before any data is sent. This is to ensure that the data is received correctly at the other end. Let's assume that the source computer wants to send 1 bit every second. It will synchronize the clock with the other computer. And this clock constantly alternates between 0 and 5 volts every second. Now, data is sent and is analyzed. If 5 volts is sent for 3 seconds, it is considered a 111. It would be difficult to analyze this information in the absence of clock synchronization as to how many ones and zeros were sent, in case one computer sends a series of ones or zeros. Let us see how the data appears while sending it through Ethernet cable, which uses alternating current or AC. Let us now have a look at how this information is actually sent as seen on an oscilloscope. In this example, you can see that the voltage is fluctuating between 1 volt and minus 1 volt. This visualization is from an oscilloscope. You can see the vertical lines that represent a gap of 100 nanoseconds, which translates to a speed of 10 megabits per second. Whenever the voltage is going towards 1 volt, it is considered a 1. And whenever the voltage is going towards minus 1 volt, it is considered a 0. You can see on the right the symbols showing the same. It is important to note that only transition from either negative to positive or positive to negative at every 100th nanosecond mark is considered either a 1 or a 0. You can see that the first and second arrow indicate a transition from negative to positive. So it is interpreted as a 1. We will not consider, however, the transition from positive to negative between these two, because that does not occur at 100th nanosecond mark. Now let us see this information in a video with more explanation. This will further help you understand how information is sent over Ethernet.
Before, you're likely going to recognize what we're looking at here. These are pictures of a cable that's used very often to connect computers to a network. And this particular type of cable is often called an Ethernet cable. What we want to focus on here is how this cable is able to carry information from one computer to another. So if we cut away the outside jacket here, we can see that the cable is made up of it's actually 4 pairs of copper wires. So there's 8 wires here total. And in future videos, we'll get into the details of why that is and what all these different wires do. But for now, let's just think about kind of the most basic way that we can imagine to use this to send information. So probably the simplest thing we can do is to just apply a voltage across two of these wires. Just so connect some voltage here. And then we can vary the voltage to send information to the other end. So for example, maybe we'll vary the voltage between 0 volts and 5 volts. And so then we can vary this over time. So if this is time going off here to the right, maybe we start at 0 volts for a second, and then we switch this to 5 volts for a second, and then maybe it goes back to 0 volts for 2 seconds, and then up to 5 volts for a second, and then 0 volts for a second, and then 5 volts for 2 seconds. And so if we look at what we did here, we've got basically two different states that this can be in. We can either be at 0 volts or we can be at 5 volts. And so we actually call these states, we have a term for this, we call these state symbols. So 5 volts and 0 volts are both the two different symbols that we have. And we call these symbols because we can use them to represent information, like a number. So for example, we could say that 0 volts is a symbol that represents the number 0, and that 5 volts is a symbol that represents the number 1. And so if we look at the voltage here once per second, we've got 0, 1, 0, 0, 1, 0, 1, 1. Which we could actually interpret this now as a binary number. If we wanted to, we could even write this number as a decimal. And so 0, 1, 0, 0, 1, 0, 1, 1, converting that to decimal, that actually equals the number 75. So I just want to take a moment and go over some terminology here. So as we mentioned, the different states here are called symbols. And the rate that we're sending these symbols is called the rate. So in this case, the symbol rate would be 1 symbol per second. You might also see this sometimes referred to as baud, and baud is a term that literally means the symbol rate in symbols per second. So in this case, with the 1 symbol per second, we refer to this as as sending this information at 1 baud. So if we were sending this 10 times faster, at 10 symbols per second, so each of these were a tenth of a second long, then we'd be sending information at 10 baud. So this is interesting. So hopefully you can see how this lets us send whatever number we want to send. But what if we want to send text? Well, since we can send numbers, really all we need to do to send any message we want is to agree on a mapping between a number and then a letter or symbol or some other character. And so one of the most common sort of agreed upon mappings is ASCII. And I got this from Wikipedia as just an example of what ASCII looks like. And it's just this table that maps between numbers and they call it a glyph, but it's basically just a character, a letter of some sort. So for example, this 75 that we had up here maps to, in ASCII, 75 decimal maps to the letter K. And you can see they also have it here in binary. And this is what we have up here. 10010111 is the binary letter for K. And so you can see that by using this mapping and by varying voltages like this, we could send any information that we wanted to.
All right, great job, everyone. This concludes the class today. Learning about these ones and zeros and bits and bytes is very, very important, and you will see it very soon. This will help you in learning some important computer concepts later on, especially while we will be talking about networking. This is a really important concept. If you found this video helpful, do share it with your friends and family, and let me know your thoughts so that we could improve further contents. Do consider subscribing so that you get notified as soon as we post new videos. Accelerate Computer Systems works for the students and startups by providing them with cost-effective, high-quality, factory-certified Dell laptops, desktops, starting at just $400. Send an email to us today for more information on the email flashing on your screen. Thank you so much for learning with me today, and I'll see you in the next lesson. Until then, happy learning.